Okay, so let's see how this is going to work. So we're going to start off by sort of dealing with this notion of time sharing and the idea of a timer interrupt. So we have a program that might want to access the time of day. And so that's something that's managed by the kernel. In other words, every time the timer goes off, it says, oh, another 1/10 of a second has passed. I'm going to go increment my data structure in kernel memory that represents the time of day. I'm going to increase it by 1/10 of a second. And then, so that's how the kernel is keeping track of what time it is. It's sort of dealing with these interrupts and saying, oh, time to add another 1/10 to the current time of day. The programs want to be able to access, the current time of day. But they don't actually try to deal with the hardware or deal with these 1/10 of a second interrupts, things like that. They basically simply will ask the kernel, what time is it? And it's the kernel that deals with all the problems of these timer interrupts and data structures associated with keeping the time of day correct and things like that. So let's see if we can follow this story along a little bit. So here's sort of the picture. So I'm going to show you code now that actually lives in the operating system, in the kernel, right? And so the first thing we have is, so here we have this big, in this case, 64-bit number that represents the time of day, in milliseconds since midnight or something like that. Then we have this user data structure, which has a little array for storing these 31 registers. So when you asked where do we store all this stuff, it's actually an array in the kernel. It's just, when you have, when you write a program, you can go off and do, allocate an array, just like you could in C or an assembly language. And here we've just written the C code that says, please give me a 31-element array. We're going to call it user, or user.regs, and that's where we're going to stick the registers. So let's see how this works. So we have this user data structure, and then this is the C code that we expect to run whenever the timer interrupt goes off. So when this function gets called, it simply increments the time of day by, well, this looks like, if we're interrupting every 1/10 of a second, it looks like the time of day is in 1/10ths of a second, because we simply increment the time of day by 1. So how do we get from the hardware interrupt to running this C code? And that's what this does. So here's the clock handler. This is the code that gets run when the timer interrupt goes off. Okay. And the first thing we can see is it carefully copies all the hardware registers into this user data structure. Okay, everybody see where this? So we're taking the contents of each of the hardware registers and copying it into this array. So now we're allowed to use the registers. Now the kernel code can use the registers. No registers were used in doing this, right? I'm not changing the contents of any of the registers until I've saved all those bits away in this magic array, this kernel array. Now I can go off. I'm not going to trust the user stack, so I'm going to set up my own stack, set up the stack pointer to point to the kernel stack, and then I'm going to just do a regular subroutine call off to the clock handler, which will do whatever it would do. When that returns, I'm going to take all the registers, which probably got messed up by the C code in the handler that I called. I'm going to restore them from my magic array where I saved them away, put them back into the hardware registers, back up the XP, because the XP was actually the PC plus 4 of the instruction that was executed. So I want to back up what will become the program counter to point to the instruction that was interrupted, so I can now actually execute that instruction. And then I go off and I say, okay, go back to that PC and start running the user program again. Right? Interrupt, save the registers, jump to the handler. It does whatever it does. When it returns, restore the registers and return to the user. Okay, a very simple little recipe. Do we have to save all these registers? Could I not save some of them? What would that mean? That would mean, of course, the kernel. Yes, go ahead. We have to save the registers that the kernel is going to change, and we don't have to save the registers if the kernel doesn't change them. But because the kernel is itself a very complex program, in general, we don't know what registers it's, the C code when it gets compiled will use. So in general, it's just simpler to write the kernel to save away all the registers. In the end, we're only saving a couple stores and loads, which in the scheme of things is a vanishingly small overhead. Okay. All right.